then turn on streaming to YouTube. So YouTube is always going to be at least 10 seconds behind, just because it takes a little bit longer for YouTube to transcode and we display the content. All right, so I hope the whole class is here. We are seeing 5 people that is watching from Discord, and probably 1 or 2 that who's going to be watching from YouTube. All right, so let's go ahead and continue from Tuesday. So what I did today was I changed my notes a little bit. So instead of having me to work on every single one of the transformations in Zeta, I have included a link over here. So if you refresh your page, you will find it too. So let me just go there. Okay, it's a Wikipedia page, or it's supposed to be a Wikipedia page.
Yeah, it just relinks to the.
Oh, that's because I did not. That's because I did not specify the link location. I only specified how it should display, and it's a different thing to actually show it. So if you guys want to go there, you can just kind of copy and paste the link here for the time being. Okay, so I'll do just that. So give me a second here to get back to the same place. All right, so I'm just gonna copy and paste this. So the link doesn't work, okay, but the URL is actually correct. It's just that it doesn't work.
There's not really anything on the wiki page.
Let me see. All right, so there we go. And it's going to example 2. Oh man, that is disappointing, because I thought it would go to the exact bookmark that it is supposed to be in. Okay. Oh, okay, that doesn't work. So let me see. Could be, yeah, the pound or the. Okay, the pound doesn't appear. That is why, because in LaTeX, the pound has a special meaning. All right, so I'm gonna have to fix that first. Okay, so the pound. Okay, I'm not sure whether that would do it or not. Let me just republish that. And then refresh the whole thing. Back to here. Yeah, see, there's a pound sign this time. The pound sign is important because it is a bookmark in that URL. So let me do the whole thing again. So it's copy the whole thing and then paste in a new window, including the pound sign. There we go. So this is much better. I will fix the link here so that the URL or the link itself, the HTML anchor, would actually work. But for the time being, I'm not going to do that. Okay, so for the time being, I'm just going to go to example 2, which is in the Wikipedia page of propositional calculus. And I'll just kind of scroll down a little bit, because that's basically what we are talking about here. This is one rule, okay, in Zeta. So what it says is, if you can find an implication, in Wikipedia, they only use a single line implication as opposed to me using a double line implication in my notes. But it says, if P implies Q, if you can find something that looks like P implies Q, and then you find something that says P implies not Q, then you can infer, okay, this the V dash symbol is known as infer that not P is true. In other words, P is false. Okay, it kind of makes sense, right? Because if the implication is true for P implies Q, and the implication is true for P implies not Q, that means P has to be false in order to make both of these implications true. Because otherwise, one of them has to be false if P is true. So we have a whole bunch of these things, and don't worry, I do not want you guys to memorize all of these. I just want to give you a link to a list to basically just show you that, yeah, there's a lot of these rules. Okay, some of these are for simplification, like all the eliminations are for simplification, And then we have conditional proof, which is kind of recursive. P infers Q infers P implies Q, and so on. So we are not gonna, and this is also a summary. Okay, this is a quick summary as a table of all the inference rules that a system is supposed to have. And you can see this is a pretty long list. Okay, this one we talked about. The second to the last one we talked about. And then the bottom one, the last one, is really the Morgan's law applied to the second last one. Okay, so the bottom line is, well, there's a lot of stuff like this, and if you were to write a program to prove a theorem, then the program has to kind of pick the right transformation rule, because at any particular time there's a whole bunch of transformation rules that are applicable. Which one will lead us to the solution? Which one will lead us to the well-formed formula that is the proposed theorem that we're supposed to prove? We have no idea, right? I mean, it would take a very experienced mathematician to look at the problem and go like, yeah, I think we should probably go that way, or then we should probably go that way, and so on. But the computer doesn't have that kind of knowledge. We talked about this space issue. I'm dragging the picture back into the recorded area, or the area where you can see. So we talked about this, where the blue area is supposed to be the entire space of all the well-formed formulae, and then the red dots are the ones that are in iota. So these are the ones that are given to you and say that, okay, these are true to begin with. Don't ask me why. I'm just telling you that these things are true. Okay. The yellow ones, on the other hand, are quote unquote derived. Okay. So when you see a green arrow, it is an application of one of the transformation rules. So this is one application, where we use something in iota in order to infer something that's a well-formed formula, but the inference basically says, well, since we're given that this is true, whatever the red dot is representing, then we also know that whatever the yellow dot is representing is also true. So this one, on the other hand, is also the result of applying just one transformation rule, but it requires two inputs. In other words, there are two items in the set of that transformation rule, and the syntax matches, and as a result, we apply the transformation rule, and now we are labeling another dot to be yellow. So the question is, when you are asked to prove a theorem, that theorem is basically just a well-formed formula sitting somewhere in the space, in the blue space. I'm labeling this one gray because it is of interest to us. We want to know whether we can eventually label this gray circle yellow or not. That is the question, okay? So when you look at this particular picture, it doesn't look too bad, okay? Because the blue space is finite, okay? We are trying to find a needle in a haystack, and the haystack has a finite volume, so it's not a problem, okay? You just have to spend the time to look everywhere. If the needle cannot be found in the entire haystack, you can conclude and say that, hey, Tack, you just tricked me. That needle, is not actually in the haystack. Okay, not a problem. But the problem, is the space of all the well-formed formulae is actually infinite. There's no end to it. Now, why does it have no end? All we have to do is to look at this particular rule here. Okay, from nothing, from an empty set, we can infer P or not P. So now we can stash P or not P, or we can put that into the well-formed formulae space, and then we apply this rule. We can apply this rule again. So now we have P or not P, or the negation of P or not P is also true, which is kind of not. It's not a very smart thing to do, but the transformation rules does allow us to do that. So that means that just using one single rule here, I can already generate an infinite number of well-formed formulae, which is problematic because now we have a space. Okay, let's go back to the analogy here. So now the blue space is actually infinite. Okay, we know the gray dot is somewhere in the blue space. That is not a problem. But because that space is infinitely large, okay, So we cannot hope to label everything. Okay, we cannot just apply every rule that is possible and then try to label everything that can possibly be labeled yellow, because the space is infinite. You cannot label everything. When you can only label one single spot after one application of a transformation rule. So that is actually the challenge. Okay, if I go back to the Wikipedia page, that is the challenge for us too. Okay, so if you are in a higher math class, okay, let's say in linear algebra, okay, and the question is to prove a particular theorem. A lot of people feel that those are the harder questions, as opposed to, okay, this is a matrix, find the inverse of this matrix. Because finding the inverse of a matrix is a tedious operation, but the steps to do that is pretty well known. Okay, you can write a program to do that. But to prove a theorem, you have to choose which rule should I use at a particular time. And at any particular time, there is a whole, I wouldn't say infinite, but there are multiple rules they can choose from. If you choose the wrong one, okay, then you end up further and further away from what you need to prove, which is a problem. Okay, it's a problem for people who are just learning mathematics, people who are just learning how to prove, and it is also a problem for a computer to deal with, because the computer also has to be able to choose which rule to apply in order to get quote unquote closer to the theorem that we want to prove. But the biggest problem is not that it will be difficult to prove a theorem that is in fact a theorem. Okay, the problem is if I give you a well-formed formula that is not a theorem, it is impossible to conclude that is the case, because I'm basically asking you to find a needle in a haystack that is infinitely large. Well, at any particular time, all you can tell me is I haven't found the needle yet. But you cannot really tell me that the needle does not exist in the haystack, because at any particular time, you can only have explored or investigated a certain finite portion of that entire space, which is infinite. So you cannot differentiate between the two cases of that well-formed formula that I gave you is not really a theorem versus that it is a theorem, but I haven't found it yet. Okay, those two cases are indistinguishable from your perspective. So what are we going to do then? Okay, well, in many other versions of this class, taught by other people, they focus on this stuff here, whatever you're seeing on the screen, because they want people to do it. My take on this is I don't want to do this. Okay, I don't want you to do this either. So we want a computer to do it. We want computers to be able to prove theorems, because that will help us validate a particular piece of code, and we know that it works, okay, without actually throwing test cases at it, because then we can mathematically prove that a particular piece of code, subroutine, or program is going to work regardless of what you throw at it. That is what we want to do. In other words, our objective is to try to get the computer to prove theorems and not to train you as a human to prove theorems. So because of that objective, now we basically go back to the notes and we say, well, this is all good stuff. Okay, I can go back and talk about section 4.1 in just a little bit. Okay, I don't want to touch on it yet. Okay, because we are now, our main topic right now is how do we get a machine to do theorem proving. So that is why we have section 5, okay? And section 5 is a pretty long section, and you can see from the thumbnail on the right-hand side that we are not even halfway through this module, because the first half is only to introduce, traditionally how people look at propositional logic, okay, intended for humans to use. The second half is intended for computers, okay? And that, I think, is why I want to have this section is because this is a computer science class, okay? Even though there's a lot of math in it, I still want to apply what we're learning to computer programming, or something that is related to computers. So section 5 starts with section 5.1, which is resolution logic. So this is a particular well-formed formula, okay? Because you can see that everything that needs two operands has two operands, right? And I'm only using the connectives, known as operators otherwise, that we have already introduced. So when you look at this, okay, I know these are all Greek letters, and okay, let me just kind of spell out the whole thing, okay, to answer Aaron's question. So this is phi. So this is phi or psi, and not psi or rho. Okay. So we have three symbols. We have phi, psi, and rho in this case. Implies phi or rho. Okay. So if you don't like Greek symbols, you can just kind of look at each one and replace it with a letter in the English alphabet. Okay, that will make it easier for you guys to pronounce it. But when you look at the derivation, okay, I can briefly describe the derivations. Okay, so I think it's kind of important to describe that. So the first line is applying the definition of implication, because implication is negating the left-hand side or the right-hand side. So I am doing exactly that, okay? So this negation here is applied to the entire left-hand side of the implication, and then this or is taking the place of the implication, and then whatever is to the right-hand side can remain the same, okay? It doesn't change. From the first line to the second line, I applied De Morgan's law, because you can see there's a negation of a and, of the result of an and. So when I apply De Morgan's law, I would negate each individual item and then change the operator of and into a or. Okay. And then from the second line to the third line, I applied De Morgan's law again. And in fact, I applied it twice. The first one is to apply De Morgan's law to this negation of an or. So we have negation of the individual components of the or, but I have to change the or to an and. That's basically De Morgan's law. And I do the same thing with the second part. And I did some cleaning up too, because this is already a negation, not psi. And when you have not psi, you just get psi back. Okay, so there's an extra step of simplification that I applied here. And then from here to here, I use the rule of identity, because anything and true is just that anything. Anything and true is just that anything. So I rewrote phi as phi or true. I rewrote rho as rho and true. Now, true can be expressed in many ways. Okay, one way to express true is pick anything or the negation of that anything. So instead of just writing this one as 1 or true, I rewrote it as psi or not psi, and then the other one is the same way. Okay, this 1 or true is rewritten as psi or not psi. And then from here to here, I applied distribution. Okay, it's just like distribution in normal algebra. You can apply distribution in Boolean algebra as well. So this was phi or psi or excuse me. Let me say that one more time. This is phi and psi or not psi. So I have phi and not psi. Okay, just one of them, and then do the or with the other one, which is phi and not psi. Phi and psi. So I also reverse the order. Applying this is the commutative law of algebra, and I do the same thing on the other side. In other words, I'm making the thing more complicated than it was originally, but it's for a reason. So now from here to here, okay, I just rearranged things a little bit and applied factoring. Okay, because we can see that there is a not phi and not psi. Okay, so not phi and not psi is over here. And there's also a phi and not psi So phi and not psi is over here. So when I look at this item and I look at this item, I apply factoring, which is the reverse of distribution. And I applied something like that to the other one, to the other terms as well. And I have one leftover term of rho and not psi left. So that's just kind of the leftover. And so is this one. Phi and psi is also a leftover term. All right, so getting back to here. So now we have not phi or phi, which is really just true. So we have true and not psi, which then simplifies to just not psi. And then over here, we have something similar. We have psi and then rho or not rho. So I just look at rho and not rho and go like, rho or not rho. And that is just true. Phi, psi and true is just psi itself. So I can now have these two. So now that we get to the third line from the bottom, we see that we have not phi or blah, 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 okay? The blah, 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 blah is now irrelevant because when we see not phi or psi, sorry, this is psi. So when we see not psi or psi, that is just true because, between the psi and the not psi, one of them has to be true. And in an or, if at least one side is true, the whole thing is true. So now we have one or true or whatever. Well, true or whatever is always just true. There's no way to turn the true to false again when all you can do is disjunction. So now we have this true in the end. So this is a long proof, okay? I'm not saying this is the quickest way to prove this particular theorem, but it's one way, okay? But the bottom line is this particular well-formed formula is always true. It doesn't matter what you plug into phi, doesn't matter what you plug into psi, doesn't matter what you plug into rho. This particular statement is always true. This implication is always true. So go ahead. I know you guys have questions.
So I just had some questions about the use of the parenthesis.
Mm-hmm.
So on the first line at the very end, you have double parenthesis, phi or rho, double parenthesis.
Yes.
Is the double parenthesis have extra meaning? Or
No, it doesn't really have any extra meaning. The only reason why I applied double parentheses here is because I want to use parentheses to enclose whatever is on the left hand side and also whatever is on the right hand side. So the right hand side already has parentheses in it. So I just put in an extra pair of parentheses just to emphasize that this side here is on the left hand side and this side here is on the right hand side of the implication.
Okay, that's what I thought.
Yeah, so the double parentheses do not have extra meaning. Okay, so Omar is asking, why do we drop the parentheses on the second line? That has to do with the associative law of Boolean algebra, which is kind of the same thing as the associative law in normal algebra. So when you say 1 plus in double parentheses, 2 plus 3 double close parentheses, the whole thing is just 1 plus 2 plus 3, because the ordering of how you resolve the nested application of or plus or addition does not matter. So we can dissolve the parentheses on the second line. So is that okay so far? Okay. Omar is typing, so I'm going to wait a little bit. Okay. That is a good question. We will cover Boolean rules in just a little bit. So in this class, CISP440, unlike CISP310, we will go over Boolean algebra because occasionally we want to do certain things by hand, and as a result, we kind of need to know Boolean algebra. All right. So now the question is, okay, fine, Tech, you have just proven that this well-formed formula is always true. So what is the big deal? Well, the big deal is you can start with 3 different things and end up with only 2 of those 3. Okay? In other words, if you have a conjunction of 2 disjunctions and one component of the disjunction on one side is the other side has a negated version of the same term, then that term just quote unquote cancels out, and then you can rewrite the conjunction of the two disjunctions without, as one single disjunction, but without the term where it is negated on one side and then not negated, it negated on one side and not negated on the other side. That is what I mean by that, okay? And some people look at this and go like, I'm still not getting this, okay? That's okay, it's not a problem. So what we'll do is we are going to look at this from a truth table perspective. I'll set up the truth table, but I want you guys to do it, especially if you are not convinced about this particular proof. So let me switch to the whiteboard area and then start to type something in that whiteboard. Okay, we got a question here. Writing out these symbols is hard. Yeah, it takes a little bit of practice to do it. Okay, so I'm going to generate a table over here. So we have row as one thing. Oops, I need to put it in the $sign. So we have row as one thing. And then we have we have psi as another thing. And then I think we have, let me just try to stay close to the notes here. So we have phi, psi, and row. Okay, so let me, okay, row is the last one. I want to preserve the same order. So we got phi to begin with. And then we have psi. And then we got row. Okay, there we go. And then I want to also evaluate these expressions. Okay, so I'm gonna type that in. So just bear with me as I type that. All right, so it is phi or psi, and then an and.
On so tack on the 1, 2, 3, 4th line, the reason why we have phi and or row and 1 is to just make it so that those will just be
From
one.
here to here?
Yes.
So from here to here, I am just setting up so that I can replace the true eventually with something that is guaranteed true, which is psi or not psi.
Okay.
Yep. Let me finish typing this. We have a or row, close paren, right arrow, and then we got psi or row. There we go. Okay, let me see whether I typed it right or not. Okay, we need a close $sign. Yeah, that looks good. Okay, so now we have 1, 2, okay, 3, 4. There we go. So now we turn this into a table.
So in that case, from going from true to guaranteed true or guaranteed false, it'd be like something like we'd be turning, say, 23 into 1 or 0, correct?
Not sure about what 23 is representing.
Like just a random value for phi or row. So instead
no, they're
of
Boolean. They're Boolean. They can only be true or false.
All right.
Yep. So to give you a more complete idea of what we're dealing with here, so we have 0, 0, 0, and then I would let you guys evaluate this one. That's the value of the expression. So we end up with like 8 rows of these, right? Because we have 3 independent variables. Each one can be true or false. So that means we have 2 to the power of 3, which is 8 rows. So I got 6 here, 2 more. There we go. Okay. And so I'm just changing it so that we can see that how we end up with the 8 different rows. Okay. So there we go. There we go. All right. So I'm not going to do a single thing about the question marks because I want you guys to do it. So go ahead and evaluate this, not during class, okay, because this will take some time, and figure out, what we have to put here, okay? And I'm going to propose and say that you're going to end up with all ones over here. So this is yet another way to prove a theorem in Boolean algebra, is to use a truth table. It is one of the quote-unquote laziest way to do it, from the intellectual perspective, because there's no need to understand algebra whatsoever. But at the same time, it is also more visual because you actually get to see, how a particular expression like this one is always true. So this is really interesting because it basically is saying, the implication, which is this operator here, is always true, okay? Regardless of how you choose phi, psi, or rho, okay? Now that is really cool because it allows us to deduce, okay? It allows us to say, okay, if I am given two disjunctions where one term of one disjunction is negated on the other side, then that really just implies a simpler term with only two of the three original variables, because psi is gone in the resulting well-formed formula. That is the significance of resolution. So are we getting a hang of resolution or not? Because,
Yeah, I got it.
okay, so resolution is really important, okay? So now that we know that this implication is always true, so now we basically say, in the mechanical system, this is not mechanical, okay? This is done by hand. So this is based on the meaning of and, or, not, implication, and so on. But since it is making sense to us, okay, logically it's making sense. So now we turn it into a rule and just say, hey, this is the only element in zeta. We don't need anything else. We just need this one rule. Now, there are other things that are kind of essential, because you kind of need to have commutative law, where you can, change the positioning of terms inside a and, inside the or. So that's kind of implied, okay? So I'm not, putting those as rules, but the idea is this is the only one that is important. Now, we don't have a conjunction here. We have a comma here because the set is already saying if I can find within either the well-formed formulae already labeled red or yellow, okay, if two of those things fit in this particular format, then I can also label this as a yellow dot, okay? So that's why, if it's already in the set to begin with, everything in the set is already connected implicitly by a conjunction. And that's why we have a comma to separate the two elements in the set and not to use a conjunction as a logical operator. So I think that portion is actually important to note and understand why that is the case, okay? So with this, we're going to change how we define a well-formed formula just a little bit, okay? So in this particular system, we only got two symbols. We only got two operators. Omega 1 still has negation, so we still need negation. Omega 2 only has or. We don't need and. We don't need implication. We don't need if and only if. We just need or, okay? So this is really kind of cool. But before we get to what is a well-formed formula, okay, we have to get to is a disjunctive element. Okay, so is ADE is a predicate. It is basically just asking, whether something can be qualified as a disjunctive element. So this particular definition here, we have seen already. Every element in alpha is automatically a disjunctive element. So you can pick anything in alpha, and that thing by itself is a disjunctive element. Now, why is it called a disjunctive element when there's no disjunction? Well, we'll see later, okay? So the next line, which is the fourth line of how we redefine what is a well-formed formula, is saying the negation of anything they can find in alpha is also a disjunctive term and a disjunctive element. So if you have P, Q, R, S, T in alpha, then P by itself, Q by itself, each one is can be seen as a disjunctive element. But if you just negate a single term, like not P, it is also a disjunctive element, disjunction element. If you look at not Q, it is also a disjunction element, and so on. So are we doing okay so far? Up to just the first 4 lines, because the next line is going to be the difficult one. But we need to make sure that the first 4 lines are okay first. So Omar is saying, would the new transformation be part of Z? Yes. So zeta only has one single rule, which is this one. So we are reorganizing a company. This is a complete reorg of a company where we had a lot of rules before. Now we only got one. But the way we look at what is a well-formed formula is also a little bit different. So are we ready for the 5th line, or the 5th item of how we qualify a well-formed formula? Are we good so far? All right. All right, so let's move on to the 5th one. So the 5th one says, okay, if you give me n phi's, okay, phi 1, phi 2, phi 3, all the way up to phi n, okay, and you tell me that all of those phi's, each individual one is a disjunction element, then the OR between all of those things is a well-formed formula. Let me say that one more time. Let me say that one more time. So this part here, okay, if you look at the left-hand side of the implication, this is basically just saying, if you give me n phi terms, and each phi term is a disjunctive element, then the second part, which is the right-hand side, is saying the disjunction of all of those disjunctive element is a well-formed formula. All right, so let's go ahead and look at some examples, okay? Because I think examples is going to be very helpful here. Okay. So make a bulleted list here. Examples of well-formed formula or not in to be used in resolution. Okay. All right. So let's start with let's define alpha first. Okay. So alpha is the usual, which is 0, 1, P, Q, R, S, T, and then the Greek symbols, okay? But I'm not going to list the Greek symbols here because the Greek symbols are not, they're not used in a normal well-formed formula. They're only used when we need to specify a rule, so I'm not going to specify the Greek letters over here. So given these things are in alpha, I will let you guys decide whether this is a well-formed formula or not. Okay, let's start with something simple. Okay, do you think this is a well-formed formula? Okay, let me ask the question here.
Yes.
The answer is yes, and that is correct. Okay, in fact, it is. Okay, so the first thing we notice about P all by itself is P is a disjunction element because P is in alpha, and anything in alpha by itself is a disjunctive element. So now the question is, can I look at P as one item inside a disjunction? The answer is actually yes, okay? Because when we refer back to how we define a well-formed formula, this n here can be 1 or even 0, okay? So that means, if you only give me one single phi, and that is a disjunctive disjunction element, then that thing by itself is a well-formed formula, because n can equal to 1. Now, when it equals to 0, it is a little bit tricky because when it equals to 0, then we end up with just false as a term, okay? Because false or whatever is always whatever. So we can always imply that there's a or false in every single disjunction. So that part is always there, but we don't usually see it. All right, so let's go back to the whiteboard, and I'll just kind of finish this conclusion here. So P is a well-formed formula under the new definition. Okay, so let's look at another one. Let's look at P or not Q. Okay, so is it a well-formed formula? What do you guys think? Well, it's an or of two things, right? So we now have to look at each thing and see if each thing that we are oring is by itself a disjunction element. P is a disjunction element because
this is true as well.
Yep, that's right. But we want to also know why the negation of Q is also a disjunction element. But why? Well, because it is the negation of one of the things that we can find in alpha. That's why. Is that okay? Does everybody understand why the negation of Q is a disjunction element?
Yep.
Okay, cool. So now we have two disjunctive elements, and we are doing a or between those two. So that's exactly how a well-formed formula is defined in this new scheme. So as a result, P or not Q is a well-formed formula. That's very good. So let's look at something else. Let's look at P and Q. Is it a well-formed formula? Well, we can say that P is a disjunction element. Okay, not a problem. In fact, I'm gonna go back and use the math form of that. Okay, so now we look at Q. Q is a disjunction element, not a problem. But we are looking at a conjunction between two disjunction elements. Wait, hold on a second here. If you look at omega 2, conjunction is not even an operator that we are allowed. Oh, okay. So that means this cannot possibly be well-formed, okay? Not well-formed because conjunction is not even in omega. Okay. All right, so let's take a look at something else. Okay, let's look at, now we know that we need to stick with negation and disjunction, okay? So let's look at another one that has those two. So now we have the negation of P or Q, and then that entire negation is ORed with R, okay? In fact, I'm going to use extra parentheses just so that we know, what the ordering of the operators, okay? So now we look at this and go like, let's see. The final OR is this guy over here. And we need to make sure that everything that we're ORing are disjunction elements. R is okay, so we'll take care of R first. R is a disjunction element because R can be found in alpha. Anything that you can find in alpha by itself is a disjunctive element. So R is not a problem. Now we look at the other side. So now we look at the negation of P or Q. I cannot find this in alpha, right? This entire well-formed formula is not found in alpha. Okay, so now we can say is not found in alpha, and the negation of this whole thing is not found in alpha either. So that means it is not a disjunctive element. Neither is the non-negated version, and hence this thing, which is the negation of P, the negation of P or Q is not a disjunction element, because one side of the final or the last OR that we need to perform is not a disjunction element, so that makes the entire thing not a disjunctive element. It's not, it's not a well-formed formula. Is that okay? Does everybody understand this part?
So, so P or Q, would that be well-formed?
Yes. So if you're just looking at this part, it is well-formed. Not a problem.
But once we knot it, then it becomes not well-formed.
Well, that is correct. This is already not well-formed, and it is also not a disjunction element. So that's why when you look at this entire thing, it is also not well-formed, because the only thing that can be considered well-formed is the OR of things, where each thing is either something that you find in alpha or the negation of something that you find in alpha. This is not something that we can find in alpha. Even if you look at the non-negative version, which is P or Q, that is also not found in alpha. Alpha only has individual symbols, but not expressions.
Okay. I think I'm a bit... So anything found in alpha is disjunctive, correct?
Anything you find in alpha is just a basic symbol. And so everything that you can find in alpha is a disjunction element. And also the negation of anything that you find in alpha is also a disjunction element. So when you look at, I'll give you an example. So S by itself is a disjunction element, and so is not S. And you can also use the constants if you want to. Okay, not very useful, but if you have a 1, in your OR, well, technically it is still well formed, although it is not very meaningful, because 1 or whatever is always 1. Or if you can say, you can put 0 into a disjunction also, but 0 or whatever is just whatever, because 0 is the identity of disjunction. So yeah, you can do that. It's not just, it's just not very helpful. Is that okay?
Yeah, but I'm a little confused on number 3 now, the P and Q.
P and Q is not well formed, because the operator and is not even in omega 2.
Oh, okay, yeah.
And so P and Q certainly cannot fit into this format, right? Because what is considered a well-formed formula has got to be a disjunction of things. And when we look at this thing here, it is not even a disjunction of things, it is a conjunction of things. Omar is correct. We can only use negation and disjunction in a well-formed formula, but the nesting is important as well, because because this one, okay, this expression is only using disjunction and also negation, but because we have a OR nested inside a knot, so that's why it is also not well-formed. The negation can only be applied to an element of alpha.
Okay, yeah, yes. That makes sense.
Yeah, so Omar is correct also. There's so no nesting whatsoever. Yes. All right. So are we getting a kind of a good idea of what is considered well-formed under new management?
Yes.
All right. Cool. So that's kind of interesting because now we say does this have a different name from the last one? What do you mean by last one? Yeah, this is a redefinition of well-formed formula, but only specific for the case when we need to use resolution. Okay, I suppose, okay, let me switch back to the whiteboard. So you can sort of call this, RWFF for resolution well-formed formula. And that's just my term. I don't think it exists in computer science or math whatsoever. Rough. Yes, RWFF. So are we good so far? If you guys want to use an example, you can put it in the text channel. Just give me an example and ask, okay, is this considered well-formed under this new management, under these new rules? And I'll be able to see it and talk about it. So that is if you guys want to do it. And you don't have to use LaTeX, because what you can do is to use the simplified way of specifying a Boolean expression. And I'm going to give you an idea what I mean by that. So the simplified way to do things is to say, is to use a plus instead of the OR operator. So if you want to say, P or Q, let me put a negation of Q over here. So let me switch back to the whiteboard first because you guys cannot see it. Okay, so if this is what you want to express, which takes a little bit of getting used to if you want to type it in LaTeX, then you can type it without using LaTeX as P plus exclamation point Q, because exclamation point is negation. You learned that in C and C++, but instead of using double bar, which is awfully confusing, I just used the symbol plus. But this plus has nothing to do with arithmetic addition. It is I'm simply borrowing, or in C++ terms, overloading an operator that you have learned in normal algebra before.
So if we take the second example, P or not Q,
this
P
one.
or Q also be well-formed?
Yes, okay, Q by itself is well-formed. So is the negation of Q, because everything that you find in alpha by itself is a disjunction element, and every disjunction element by itself is also a well-formed formula.
Okay.
So if you negate it, it is still a disjunction element, and as a result, it is also a well-formed formula. So not R by itself is a well-formed formula as well.
Cool.
All right, cool. All right, so that means from here on, anything that is well-formed can be a gigantic OR, where each item that we are ORing is either a term or a symbol that we find in alpha or the negation thereof. And everything is flat, okay? There's no nesting, as Omar said. Okay, there's no nesting whatsoever inside the OR. The only thing can nest is the negation. Okay, so you can say not, but when you say not, you can only say the negation of one of the things inside alpha. So whatever you are notting, whatever you're negating, cannot by itself be an expression that has OR in it either. Okay, so now we are looking at some kind of restriction, okay, right? Because this is a lot of restriction of what we can consider well-formed at this point. So now the question is, can we convert any Boolean expression that was considered well-formed before we decided to change the rules into something in this current format? That is the question. Okay, so let's go ahead and take a look at something as an example, okay, from before. And let's see. Now there's a long example in the notes too. So if you want to look at the long example, it's 5.2.1. But instead of using that one, well, I don't know. Do you guys want to look at that one, or do you want to look at something different? Let's look at this one first. Okay, so let's look at section 5.2.1, which starts off with a kind of general Boolean expression that would have been considered well-formed before we changed the rules. So now the question is, now that we changed the way we define what is well-formed, does it restrict what can be expressed? That's the big question, right? So let's look at this guy over here. And then we use Boolean algebra to derive a whole bunch of things. So let's look at the first line versus the second line. So the first line versus the second line is using the definition of implication. See how R implies Q becomes not R or Q. That is the definition of implication. And then from the second line to the third line, I applied De Morgan's law. The negation of an or becomes an and, but I changed all the individual terms that we are in the or into the negated version of that. And then from the third line to the fourth line, I did a simple simplification here, because the negation of R is really just R itself. Okay. From the fourth line to the fifth line, I applied distribution. This is also known as FOIL for those of you who understand the FOLE, of algebra, normal algebra. So if you considered an and as a multiplication and an or, no, I take it back. It's not FOIL. It is really just a normal distribution. So we have, basically R and not Q and P because of this here. And then we have an or. The or is R and not Q and T over here. So this is just a normal distribution. It is not a FOIL. A FOIL needs two things on both sides, and then we basically do the cross product thing, which is kind of what a Cartesian product does. And then from here to here is a FOIL. This is a three-way FOIL. So we got three terms on one side, and then I'm just looking at, let me see where I can see myself, because I need to make sure that my fingers are in view. So we got three things on one side, and then we got three things on the other side. And we need to do basically this time it is a true Cartesian product of those three. So we can choose one of the three things over here, choose one of the three things over here, and then do an or between those things. And then we take every single thing that we have ored and take a huge gigantic conjunction between all of those things. All right. This normally cannot be done in normal algebra, because if we look at conjunction as multiplication and disjunction as addition, you cannot do a FOIL between that. But in Boolean algebra, you can. Okay, so let me just kind of illustrate what I mean by in Boolean algebra, you can do that type of distribution. So there are two rules of distribution in Boolean algebra. In normal algebra, there's only one, but in Boolean algebra, there are two. So in Boolean algebra, you can have, PQ. Okay, PQ. Okay, the easy one is the one that we know in there's an equivalent form in normal algebra. So we have P or Q, and then the whole thing and R. Now this is using the shorthand. Do you guys want me to use the shorthand or not to use the shorthand? I can do either one. It's just a little bit more typing for me, but it's not a big deal. So I just want to see what you guys want to do, because I can replace the plus with a normal or operator and then put in the and operator over here. But I can also do this, which is a shorthand that's it doesn't take as much time to type. But it doesn't make that much difference to me. but I want to make sure that everything is clear to all of you. Okay. The difference is just notation. So in other words, I could have typed this as P or Q, and then the whole thing and R. It's just a matter of, do you have a preference of, which way you want it to be expressed? It's kind of interchangeable. In the next exam, you guys will have to type these things quite a bit. So my advice is to switch to the simplified representation so that you don't have to spend too much time to type this here. So that's my recommendation. But some people may get confused, at least initially, and thinking that this really is addition. But no, it is not really addition. This is just me borrowing the addition symbol to mean disjunction. And then this is not actual multiplication. It is actually conjunction. So it's up to you guys. I guess for the time being, I'm not going to confuse you guys using the shorthand notation. We'll just use the longhand notation then. Okay, so using the longhand notation, this whole thing is the same thing as P and R or Q and R. So that's one distribution, which is kind of consistent with what you already know in normal algebra. If you replace this with normal addition and replace this one with a normal multiplication, you will see that, hey, yeah, this is the same kind of deal that we have in normal algebra. But in Boolean algebra, there's also the reverse of this. Okay, if you have P and Q that is nested, and then you have a OR R on the outside, you can also distribute this. This becomes P or R and Q or R. So both of these apply in Boolean algebra, but in normal algebra you only got one that works. Okay, so I just want to make sure that you guys know about the distribution rule in Boolean algebra. So do we have any questions about distribution in Boolean algebra? Okay, I'm not seeing any questions.
Looks good.
Okay, but I think I can sense someone thinking, but that doesn't make sense. I don't think so. Okay, this is kind of like Sherlock Holmes in the BBC version of Sherlock. In the modern version, Sherlock. Huh? Sorry.
The one with Benedict Cumberbatch?
Yes. So he can basically tell someone else is thinking in the room, and he would tell that person to stop thinking because he is the one who's thinking, and other people thinking is interfering with his thinking. So I can kind of tell that some people look at the second law, the second form of distribution here, and is having some doubts about that. Okay, and that's all. That's just completely normal. Okay, there's nothing wrong with that because it doesn't seem to make sense because it doesn't work in normal algebra. So how do we prove this? What do you guys think? I have already talked about the proof technique that will also work in this case. Can someone tell me how we can prove that P and Q, the whole thing, or R, is really the same thing as P or R, the whole thing, and Q or R, the whole thing? Come on, you guys can do this. It has nothing to do with Google. It's something that you can do on your own.
Could you restate that? So
okay, how do we prove this equality? This is something that I claim, right? And obviously it is not making any sense unless you have been doing Boolean algebra for a while, because there's no equivalence of this in normal algebra. So if someone is not convinced about this equality and go like, I don't think so, Tak, I think you're just...
we could make a table.
Exactly. Okay, so the way to prove this particular axiom, maybe I'm wrong, but it looks like the same distribution as in algebra. No, only one of them is the same. Because if you look at OR as an addition and as a conjunction as a multiplication, the first rule is the one that you see in algebra, okay? But the second one doesn't work in normal algebra. The second one is equivalent to P times Q plus R being the same as P plus R times Q plus R. That doesn't work in normal algebra. The first one does, but the second one does not. I'm looking at Omar's reply. Okay, but in Boolean algebra, it does work. So what you need to do is to borrow this table, add one more column, okay, and then have this column here, replace it with one side of the equality. Let's just say this side over here. Add one more column over here, and have that column to evaluate the right-hand side of the equality. What you should find would not be all ones in this case, but with every single row, these two columns would have identical values. If one is 1, the other one's going to be a 1. If one is a 0, the other one has to be a 0 as well. So I'm going to leave it up to you guys to do this, okay? Because it's not really that hard to do. I mean, it's relatively easy to do. But by doing it, okay, by actually doing it, yourselves, I think you will learn the technique a little bit better, and you get a sense of how things are equivalent in that case. And Omar has a very good question. Why do we compare conjunction to multiplication and disjunction to addition? Because they have resemblance. So if you look at conjunction as multiplication, and you look at disjunction as addition, and you look at true as 1, and then you look at false as 0, you will see similarities, okay, between algebra and Boolean algebra. Certain things just go like, hey, this works sort of the same way as that. It's just like, 0 is the identity of normal addition. So 0 plus 5 is 5, right? 0 plus negative 20 is negative 20. But if you have false or whatever, it is the other thing. It's the whatever, because 0 is, or false, acts like a 0 in addition. When you look at true as 1, it kind of works out too. Because when you say, I don't know, okay, so true is the identity of conjunction, just like 1 is the identity of multiplication. So they kind of work out that way. So what I'm talking about here, I think Yalez is gonna like this one. Okay, so what I'm talking about here is called abstract algebra. Abstract algebra. There we go. So if you look up abstract algebra, and I cannot spell, I just type in abstract. Okay, so bad spelling there. Thank you, Google, for being able to fix my typing. So abstract algebra is a branch of math. Typically, it is not needed for computer science people to take that class. It's the equivalence of, I would say, in a 4-year university, abstract algebra is sort of equivalent to CISP440 or CISP310. It is known as the Great Divide in a very nasty sense. Basically, people who can pass that class in abstract algebra, they will find other classes in mathematics okay, and they'll be okay as math majors. And people who cannot get past abstract algebra should not be math majors, because abstract algebra is exercising the kind of abstract thinking and understanding of concepts that really is needed for a math major. Now, they do not, what I just said, okay, does not apply to computer science majors, okay? But if you want to double major after you transfer to a 4-year university in math, then you might want to take that into consideration. To me, abstract algebra is a fun class, okay? It's just a whole lot of fun. They talk about field, they talk about ring, they talk about group, which are systems, okay? They're systems based on identities, based on what is considered a plus, what is considered a multiplication, and stuff like that. And then they can classify things into different subsystems, and then within each subsystem they can prove theorems. But the whole thing is, because it's abstract algebra, so when you look at the symbol called 0, it really is not the value of 0. It is just a symbol which is known as the identity of addition. But when you see the addition operator, it is also not really addition. It is just an operator that follows certain rules. And so that's an interesting class. And this is the long version to answer Omar's question of why I made those comparisons. So it has to do with me having taken abstract algebra and thought, hey, this is kind of cool stuff. Okay, Omar is typing again. In many ways, abstract algebra also connects with C and C++. Well, not regular C, but C++, because in regular C, in C++, okay, take back the C reference, C++, okay, but in C++ you can overload operators so that when you see the plus operator, it doesn't actually mean plus anymore. Okay, you can redefine what it means depending on the type. Okay, and Omar typed, okay, they're similar in many ways, but not all, and hence the Boolean distribution. Yep, that's right. That is correct. All right, so let's go back and continue with this over here. So that's distribution, and if I go back to the module, of course I have no idea where I was. And now that I'm looking at this, I kind of have an idea of where I was. Okay, we were talking about the distribution here, okay, because we got 3 things on one side of this OR, we got 3 things on the other side of the OR, and these 3 things are connected by conjunction. These 3 things are connected by conjunction. So I just do the distribution, and it has 3 on one side, 3 on the other side, so we end up with 9 terms. 3 times 3, which is 9 terms. Now, you look at the 9 terms and go like, oh man, that's going to be horrible. Well, sort of, right? Because I can pair this R with this R, or with this not Q, or with this T. Then I can pair this not Q with this R, with this not Q, and then with this T. And then I pair this P with this R, this not Q, and also this T, and end up with 9 terms over here. Now, the nice thing about these 9 terms, okay, but that's not it, okay? I did one more distribution, which is distributing this entire conjunction with this over this not P. So that now we still have 9 terms, but each term has 3 items in it. Okay, but we can do simplification because not P or R is just R. So we can do a little bit of simplification here. This one we cannot simplify at all, and some of these are very simple or easy to simplify. So let me pick one that is really kind of easy to simplify, like this one over here, because this one has got a not P, it also has a P, and they're inside a disjunctive term. So we can now just say, hey, the whole thing is going to be true. I don't even care what is Q or not Q, because if we have P and the negation of P, one of those terms has to be true, and since everything is inside the OR, so the entire OR has to be true. Okay, so the last 3 terms are all kind of falling into that area because we have not P or P as components of every single one of these. So we have 1 or 1 or 1. So now we just have to look at the other terms. Now when we look at these other terms, the simplification seems kind of like, well, can we really do that? The answer is yes. Okay, so let me just emphasize which part we're looking at here. We simplify these 2 into just not P or R. Okay, so let me just be more specific here. We have not P or R and not P or R or not Q. In other words, they share a common part. Okay, this is basically quote unquote, okay, I shouldn't use the word subset, but it's similar. Okay, this disjunction, this entire disjunction is a component of this other disjunction. And in the case of an AND, it can be simplified. Okay, so once again, you can make a truth table to convince yourself that that is okay. Okay, no matter what the value of P or R or Q are, this simplification works. Okay, so let me illustrate what I mean by that over here, because I do want you to kind of understand this. So simplification of disjunctions in a conjunction. Okay, it's very specific though. So let's say we refer to x, y, and z this time. So okay, on one hand we have x or y, okay, and then this whole thing is ended with x or y or z. Okay, so we have three independent variables here. We have x, y, and z. They're all independent. In other words, when one is true, it has no implication of what the other ones should be. So now I say that, hey, this whole thing really is just boiling down to x or y. In other words, this term here is useless. Okay, so you can try to prove this using one of two ways. You can look at this and say, okay, I think intuitively it makes sense. Okay, because if whatever x or y, if x or y is true, then this whole thing has to be true too, right? Because this whole thing just has x or y, and then you have or something. Okay, not a problem. On the other hand, if x or y is false, okay, if x or y is false, this still may be true, because if x or y is false, z itself can be true, but the entire conjunction is going to follow x or y, because if you have x or y being false, it doesn't matter what this thing is going to be, the whole thing is going to be false. So now we take a look at the other way around, which is basically saying, what if x or y or z is false? What does that mean? Well, that means x or y has to be false too. Okay, but the best way to prove this is once again using a truth table. Okay, which is going to look something like this. Okay, you have x, y, z over here, the left-hand side of the equality over here, the right-hand side of the equality on the fourth column, which is not in this table yet, and then you work out every single cell, and then you will find that for each row, the two expressions will give you the same result. Okay, so this is a step of simplification that I used over here. So that's why I can fold this term into this one. I can also fold this term into the first one, and then I can fold the second last term to the last term, and we only ended up with these two terms over here. All right, but the idea is, oh, so that means if I'm given a general Boolean expression like this, with nesting, with and, with implication, and all the other things that I cannot do in what is considered well-formed up here, I can transform that into something that is well-formed. And somebody's going to say, but Tack, this is not well-formed because there's an and over here. It's okay. Just replace the and with a comma, and then put braces around the two elements, the two items, and we're good to go. Because we just basically say that we have two well-formed formula. One is not P or R. That's one well-formed formula. We have another well-formed formula, which is not P or not Q. That's the other well-formed formula. We have two individual well-formed formula. Both are true. If this whole thing is true, then both of these things are individually true, and so we can just look at these two as two separate well-formed formulae that turn out to be true at the same time. And therefore, we don't need this conjunction, because everything in the set are known to be true to begin with, or are known to be true. Not always from the beginning, but they're known to be true. But the point is, I claim that I can turn anything like this, turn anything that is a valid, normal Boolean expression into something that looks like this. Okay, we have well-formed formulae, excuse me, well-formed formula, and well-formed formula, and well-formed formula, and well-formed formula. The and just kind of goes away, it dissolves, okay? But the individual terms, each one is a big, gigantic, potentially gigantic disjunction, is well-formed. So I couldn't quite get to proof by contradiction, okay? So proof by contradiction is a very powerful tool, okay? I couldn't quite get to it because it is down here, section 5.4 talks about proof by contradiction, and it is a proof of proof by contradiction itself. And I think definitely I messed up here somewhere, okay, so I'm going to have to fix that. But today's road-taking word is based on proof by contradiction. And that's why, I up to this point, I could not mention that word because I'm not quite there yet. All right, so proof by contradiction. So the passcode of today's road-taking activity is dogma. Okay, you can type it with an uppercase D or lowercase d, but it's dogma. So people, some of you, okay, not all of you, some of you just want to get lunch, which is completely understandable. I don't have a problem with that, and you can go get lunch now. It's okay. But for those of you who want to know why I chose the word dogma when I wanted to talk about contradiction or proof by contradiction, no, we have not gone back to talk about completeness and soundness yet. So that's one thing that we have to do next Tuesday as well. But okay, but thank you, Omar. I need somebody to remind me that I have not talked about something that I thought I would have time to talk about. But we'll have to get back to that one. But the question is why I chose dogma as the word. Because hey, how does dogma has anything to do with contradiction? Does anyone want to guess the answer? All right, Aaron is typing. Nobody else is typing. And oh, okay, Omar is typing too. And so is Joshua. Very good. Proof by contradiction, Professor Fox's favorite kind of proof, but he doesn't like dogma. And Alex is right, okay? Dogma does refer to the religious sense of dogma. Dogma means strict rule, yes. And Joshua is correct. It has to do with the movie, yes. Because you have to watch that movie to understand the power of contradiction. Because that whole movie, the two bad angels were about to do something that's horrible, okay? They are about to destroy existence itself by using, guess what? Contradiction. Great movie, by the way. I was really sad when George Carlin passed away because I think he would make a very great president. So between him and Stephen Colbert, I think we'll have the necessary leadership for the United States. Oh, it's definitely worth watching. And yeah. I'm not going to say any more. To say any more may not be politically correct. Joshua is correct about that too. Comedians as leaders can be scary, but it depends on which one. All right, good day. So I'll see you guys on Tuesday. Have a nice weekend. You do have the relation homework due on next Tuesday, so don't forget to work on that one. And try to read ahead of me a little bit, okay? So try to read the section that talks about proof by contradiction. Oh, okay, I didn't know that. The Dogma 95 film movement. Huh, okay, I will check that out. All right, so I'm going to stop the live stream now, but I will continue to look at the text channel because it is my office hour now. All right, you guys have a nice weekend and see you next Tuesday.